We're going to work through problem 4.2 from Taylor's Classical Mechanics. This is from chapter 4. This is a problem on work. We're going to evaluate the work done by a two-dimensional force along these three paths from the origin up to this point P. We're given here that the point P is at 1, 1, Q is at 1, 0, and this is our origin. We know that path A is going to first travel along this x-axis and then travel upwards to meet that point 1, 1. So we can start by evaluating path A. Like it says here, you can divide that into two pieces, traveling from the origin to Q and then up from Q to P. So we're going to start on A. We know that our force is x squared I plus 2xyj and our work is going to be from O to P of F dot dr, which is same as evaluating that integral right there. So let's first create an integral to represent this path here. We know that y is going to be 0 throughout this first distance that we're going to move along, and our x will vary. So we can set this up by going from x equals 0 up to x equals 1 along our path, which is just going to be that force on x, which is x squared, dx, that's our x force, plus the force on y, zero up to y equals 1. This covers our second path along the way. So this is when we're moving from Q to P. So this first integral covers our movement from O to Q and then from Q to P. Because they're two different movements, we're moving in the x direction, we only need to worry about this x integral. Moving only in the y direction, we're only going to need to worry about this y integral. And throughout this process, in the second integral from Q to P, x is going to be a constant 1. So that y force will just turn into 2y dy. Evaluating these integrals, we're going to have 1/3 x to the third from 1 to 0 plus y squared from 1 to 0, and that will evaluate to 1/3 plus 1, 4/3. So that's the work done along our first path A. We're going to go ahead and move along to part B. B is asking us the work done if we travel along the path y equals x squared. So this line is y equals x squared. That's this line here going straight from O to P, not dividing it into two separate parts of x and then to y. We will instead be traveling from O to P along that path. In order to accomplish this, we're going to move from x equals 0 up to x equals 1. Still going to split the integral like this on the path x squared dx plus the integral of y equals 0 to y equals 1 on that force of y evaluated when y equals x squared. So when we have a y, we're going to plug in an x squared dy. Now, there's a couple ways you can do this. The way that I would recommend doing it is going from x equals 0 to x equals 1 of x squared dx plus, here's where things get interesting. We're going to take our f of y when we plug in x and x squared. So x for x squared for y. We end up with 2x to the third. Now, if we say y is equal to x squared, then dy must equal 2x dx. So by plugging these things in, we can get everything in terms of x. So this second one will go from x equals 0 to x equals 1. And that'll be 2x to the third. And our dy is now transformed into 2x dx. So this can all be written as one integral from x equals 0 to x equals 1 of x squared plus 4x to the fourth dx, which is 1/3 x to the third plus 4/5 x to the fifth. All of this evaluated from 1 to 0, or 0 to 1. That's going to be 1/3 plus 4/5, which is going to be 5/15 plus 12/15 equals 17/15. And that's the work done along path B by that force. It's a two-dimensional force working along these two-dimensional paths. So, part C we can move on to. This has parameterized x and y. So we're given path C, which is represented here by this curvature. We're still traveling from O to P, so it's the same endpoint, same starting point, just traveling along a different path. So the force being non-conservative in this case, the force is producing different values of work. The path is given by x equals t cubed. So we know that the path is x equals t cubed, y equals t squared. So we can start by making our substitutions here that we're going to need. Dx is going to be 3t squared dt. Dy is going to be 2t dt. And we know that at the end, we're going to have t equals 1, and t equals 1 is going to give us our 0.11. So we're going to need to rewrite our forces here too. So our force, x squared, 2xy. So force equals x squared I plus 2xy j. We're going to transform that into a force with t being our variable. So everywhere we see an x, we're going to plug in a t cubed. So that's going to be t cubed squared, so t to the sixth I plus 2 times t to the third times t squared. So 2 times t to the fifth j. Now we can go ahead and evaluate the same way we've been doing. The work along that path C is going to be the integral from t equals 0 to t equals 1 of, first we'll take our x force, which now is in terms of t. So t to the sixth times our dx, 3t squared dt plus, we'll combine these all into one integral in just a moment, plus our y force times our substitution for dy, 2t dt, and we're going to get work along the path C is equal to the integral from t equals 0 to t equals 1 of 3t to the 8th plus 4t to the 6th dt. That's going to be 3 over 9 t to the 9th plus 4 over 7 t to the 7th evaluated from 0 to 1. So we're going to have 3/9 plus 4/7, which is 1/3, plus 4/7. It's going to be 7/21 plus 12/21, which is going to give us 19/21. That is our work in the C direction. So we found all three parts of the problem. And you notice that the work is path dependent. It's not path independent, which means that the force is non-conservative.